Hello. Um, Today we shall be speaking about an important subject, which is finding the extrema of functions. The applications of calculus are endless, numerous, and versatile. Calculus enters in all sorts of applications. Since there are variations, therefore you have to apply calculus. But then what we have done before, all the applications that we have exposed are either the Taylor expansion of functions and the summation of series, and some other applications like finding the limits, for example, using L'Hopital rule. But this is one application that it is used often. In all fields, you need to find the extrema of function. In other words, you want to maximize or minimize a certain objective function. And in this case, you have to use calculus. So in this lecture, we are going to study in detail what we call the function extrema. This is the subject called optimization, or enters into a subject called optimization. In other words, you optimize your function. You want to find the variable inside your objective function in order that the function attains an extrema, in other words, a maximum or a minimum. Now, in this lecture, we shall be focusing on first what is meant by local extrema, and then we shall list the local extrema test to find these extrema, and then finally we shall talk about the absolute extrema. Now, about what is the definition of a local extrema? What is meant by a local extrema? Local extrema, they resemble very much the tops of a hill. You have so many hills, and the local top, each of these hills had a vertex, in other words, a point which attains its maximum. But there are so many hills. Each of these hills is local, because if you add up all these hills together, you've taken them all together, so the maximum of all of them is called the global extrema. In other words, this is the absolute extrema, the absolute maximum. But each one of them is still, it's an extrema. Why it's an extrema? Because it attains a certain maximum relative to the ones which are nearby these extrema. And this is why they're called the relative extrema. They are relatively maximum, relatively higher with respect to the ones which are in the neighborhood of this maximum. So this is the definition of extreme value. Now, in order to obtain these extrema, there are many results that pertain to the extrema of functions. Now, as I said, there are two things, the local extrema and the global extrema. Well, usually, when you say extrema, you mean global extrema, and the maximum of a certain function is called an extrema. Now, there is a theorem, and we've seen this theorem in our lesson of continuity, lesson, I suppose, number 10, when we said that one of the applications of continuity is the extreme value theorem. And the extreme value theorem tells you that a function, if it is continuous and defined on a closed interval, then surely it must attain a maximum. It has a maximum at a certain point, and it has a minimum at another point. Now, this maximum, this extreme value theorem, unfortunately, provides a sufficient condition for the existence of a maximum and the minimum, but it is not necessary. In other words, a function may not be continuous, it can be discontinuous, or defined an open interval, and still it has a maximum or a minimum. So the maximum and minimum value of a function f are attained in a closed domain if it is continuous. In other words, if function is continuous on a closed domain, surely it has an upper, or it has a maximum and a minimum, and this condition is a sufficient condition only, but is not necessarily, in the sense that the function may not adhere to these conditions, and yet it has a maximum or a minimum. For example, this function here, y is equal x squared, which is defined on the open interval from -1 to 2, it has a global minimum at the point x equal to 0, and yet it is not continuous on a closed interval. On the contrary, it is defined on an open interval. Now, we have to define first the meaning of a local maxima or a local minima. Now, the meaning of a local maximum is that the function has a maximum relative to its neighboring points. It has a maximum at a point, and this point is contained in a neighborhood, or in an interval, is an open interval, and this point is an interior point, and this is absolutely necessary. This point is an interior point. And the local maximum, it means that at this point, the function attains a maximum relative to the other points in the same interval. So f of c is called a local maximum if there exists an open interval, a, b, subset of the domain of f, which contains the point c, which is an interior point then, such that f of x is less than or equal to f of c for all x in this open interval, and therefore we can say that c, it's a point at which f attains a local maximum. Now, here is a demonstration of this local maximum. Now, here is an open interval in the domain of the function, which like is drawn here, and c is a point in this neighborhood, and c is an interior point, and at this point c, the function attains a local maximum. Why it's local? Because there may be other maximum greater than this value f of c, but yet in this special small interval, f of c is the maximum in this whole interval, and in other words, it's relatively maximum with respect to the rest of the points in the same interval, and this is why we call it local maximum. And the same thing, f of c is called a local minimum if there exists an open interval, again, subset of the domain of f, containing the same point or another point c, such that f of x greater than equal to f of c. In other words, f of c attains the lowest value, f of c is the lowest value attained at this particular point relative to the ones that are in the same neighborhood. So we say that c is a point of a local minimum. Here again, here this point c here, f of c is the smallest value in the neighboring area relative to the ones in the same interval AB. Now, these is a nice demonstration of, suppose for example you have a set of hills or a set of mountains. You have so many mountains in a certain area, and you wish to locate the local maxima and the global maxima. Now, the local maximum are, you take every piece, you investigate any piece, any interval. You try to scan the whole land, and when you scan the whole land, you find that there are many local maxima. There are many tops of hills. This is one hill here, this is another one. And in this hill, the local maximum at this point here, in which the function attains a maximum, but it is not the maximum among all maximum, because you may have other places where there are higher hills. But if you consider this particular point here on the x-axis, at this point, if you take any neighborhood of this point, then you see that this point is the point at which the function attains a local maximum. What do you mean by local maximum? In other words, relative to the ones that are in the same neighborhood. So this one, in fact, is the function attains a maximum, reaches a maximum relative to the ones around it or in the same area. And same thing here. This is again another local maximum. This point also is a local maximum, but the function is not continuous there, because we said that the extreme value theorem, it guarantees a sufficient condition for the existence of a maximum, a global maximum, but it's not necessary. The function may not be continuous, and yet it has a maximum. This one is a local maxima, because the function here, the maximum is greater than the ones in the same neighborhood. This one here, the function is constant. You may consider it a local maximum or a local minimum. Whereas here, this point here, it's a local minimum. Why a local minimum? Because the function attains a value which is smaller than the one near to it. And same thing here, and same thing here. Whereas if you are interested in the global maximum, then you have to scan the whole area to look at the maximum value among all the local maxima. But of course, this is not always the case, but we assume this is so. In other words, you have to scan the whole mountains in the area and to see the maximum among them all. And this will be the global maximum of f. Now, this is a theorem which tells you when does a function has a local maximum. Now, a function has a local extrema, whether a maximum or a minimum, at an interior point. In other words, if your point is not an interior point, you can't say that the function has a maximum, a local maximum. So it has to be, function has to attain a local maximum or a local minimum at a point which is an interior point to the domain of f. And at this point, either the derivative is 0, like you have a stationary point, or the derivative does not exist. Like, for example, like this. You may have, for example, something like this. This here, the point here, derivative does not exist, but you may have also a stationary point at which the derivative is equal to 0. So either the derivative at C, at the point C, is equal to 0, or here the derivative does not exist. And these 2 points, at these 2 points, they are called critical points. In other words, they are points in the domain of the function at which f dash either it's equal to 0 or it does not exist. And if there are no critical points, then there are no local maxima of the function. Now here, this is a function, and you wish to calculate the critical points. You differentiate it, and then you set the derivative to 0, which means that you have one critical point at x is equal to 2, and another one at x equal to -4. Whereas here, you have a point, although it lies in the domain of the function, in other words, it's an interior point, but at which the derivative does not exist, but still it is a critical point. In other words, the function may have at this point a maximum or a minimum. We don't know yet. We have to do some tests. But in any case, these are 3 critical points of the function because they lie in the domain of the function and at which either f dash exists and it's equal to 0 or it doesn't exist. Now this is another example. It's a nice example here. You have a function which is equal to f of x, 2x minus 10x, and you want to reach for the critical points in the semi-closed interval from pi by 4 to minus pi by 4. Now when you differentiate it and you set it to 0, the derivative of 10 is sec squared. You have 2 roots here, minus pi by 4 and pi by 4. Are these critical points or not? No, they are not critical points. Why? Because minus pi by 4 does not lie in the domain of the function, and therefore it's not a critical point, whereas pi 4, although it lies in the domain of the function, but it is not an interior point, it's an end point, and therefore this function has no critical points. In other words, the first does not lie in d of f, yet the second lies in the domain of the function. It is not an interior point, and therefore f has no critical points. Now, what are the tests for local extrema? We have seen before that you may reach a local extrema at a point at which the function is not continuous. But it is not those points that we are interested in. We are interested only in the point at which the function is continuous. So if the function is continuous, I mean, in other words, these tests are meant to be applied only for functions that are continuous. There are many tests. One of them, which is the easiest, is called the first test. F is continuous at the critical point C and differentiable in open interval containing C. And you disregard. Why you disregard this point? Because your function may not have a derivative at this point. F dash may not exist at C, yet C is a critical point, and therefore you say you disregard this point. Then, if f dash changes signs from positive to negative, it just means that this is a maximum, of course, because it was climbing and then it's going down. Whereas if f has a local minimum at C, then the sign of f changes from negative because it was going down, then it goes again up. So this is a local minimum. So these 2 tests give you the conclusion that you are either having a local maximum or a local minimum. Like this one here. Here you have f dash positive, so the function is climbing, and then it decays again, it's going down. So this is a maximum. If f dash changes from positive to negative, while if it changes from negative to positive, then we say that the function here has a local minima, and here it has a local maximum. For example, this is a function here, and you wish to locate the extreme, the local maximum. What you do is that you differentiate, you get this one here. Here, f dash is 0 at x equal to 2, and 2 lies in the domain of the function, and therefore, because the domain of the function here, it is R, and therefore, x equal to lies in this domain, so it's a critical point. And again here, the point x equal to 0, at which the function has a cusp. We've seen this in the derivative in the lesson of differentiation, number, I suppose, 11, in which the function may be continuous but not differentiable. This is a point at which the function is not differentiable, yet it's a critical point because it lies in the domain of the function. So here you have, again, 2 critical points, one at 2 and one at 0. Now you wish to know which is maximum and which is minimum. All you have to do is to test the sign of f dash. So here before the point 0, the sign was positive. And then it went again to negative. So when it's positive to negative, so it means it's a local maxima. Whereas on the other side, here at the point 2, it was negative. And then it went again to be positive. So since it was negative then positive, so this is a point of local minima at the point x is equal to 2. Now, this is the first test to find the local extrema, but you may have also other tests. The other test is that you rely on f double dash, the second derivative, because since f dash changes from negative to positive, so it means that f double dash is what? Negative or positive. It's positive, of course, since it changes from otherwise it increases, f dash increases. But if it changes from positive to negative, then f dash decreases, so f double dash becomes negative. So which means that at the point of maximum, you have f double dash which is negative, and at the point of minimum you have f double dash which is positive. So it says this is the second test, but provided of course that f double dash exists. If f dash does not exist at the critical point, then surely f double dash does not exist, and you cannot rely on this test. So if f double dash exists, but it's not 0, because the test fails if f double dash is 0. So you have, in other words, it is meant to be mainly applied to points that are stationary points. So if f is differentiable in an open interval containing the point c at which f dash is 0, so you go pursue for the second derivative. If it exists, then you say that if it is a point of local maximum, then f double dash is negative, whereas if it is a point of local minimum, f double dash is positive, and the test fails if f double dash is 0. So now you have two tests to check for the existence of a local extrema. Now, this is one nice application of the local extrema. Here you have the function f, and here you have f dash, and here you have f double dash. Now, this gives you the meaning of the inflection point. What the meaning of inflection point? Now, the local extrema are the points at which, you have to realize this, the point extrema are the points at which f dash either exists and it's equal to 0, or it doesn't exist at a critical point. And then you test for whether it changes sign from positive to negative or from negative to positive, and then you say this is local maximum or minimum. But then you remember in our last lesson about concavity, upwards and low and downwards, we said that a point of inflection is the point at which f double dash is 0 or either it does not exist, and it isolates two regions at which the f double dash is positive or negative. So actually it resembles very much the test for the local extrema. There you have an f dash which is 0 or doesn't exist, and here you have f double dash that is 0, does not exist for the existence of an inflection point. There f dash changes sign from positive to negative or from negative to positive, and here again for the inflection point f double dash isolates region in which f double dash is either positive or negative. So actually they exactly are the same. So what does it mean this? It does mean that the point of inflection is the same point at which f dash has a local extrema, and that's it here. Here you have f, and here you have f dash, and this is a point of inflection, and you notice directly that at this point of inflection f dash is minimum. Why? Because f double dash here, this is f dash. Where is f dash has a local extrema? Any function has a local extrema if f dash is 0 or does not exist. Here, f dash, when f dash has the second derivative equal to 0, it means f dash itself has a locus extrema, and that's true. F dash has a locus extrema. In other words, f dash, the derivative of which is 0. So here, f double dash at this point in 0, it means that you have an inflection point, and then f double dash, which is the derivative of f dash, here it's negative, and here it's positive, and it's true. So f double dash here is negative concave downwards, and here is positive in concave upwards. In other words, the point at which f double dash is 0 or does not exist, and isolate two regions of concavity, upwards, downwards, is the same at which f dash itself has a local extrema. So the meaning of inflection points now is not only that you have a turning point of the curve of concavity, but it relates also to the extreme value of local extreme value of the original function f dash, of which when you differentiate it, you get f double dash. Now, the meaning of absolute extrema. Now, we thought that local extrema are the upper or the top of the mountains. You have so many mountains, and each top of each mountain, you can consider it as local extrema. What about the global extrema of the function? Now, the global extrema of the function, one directly thinks that the global extrema is the maximum among all local extrema. In other words, you scan all the mountains to know which the extrema, and then you take the maximum of all these local extrema, and you consider it as global extrema. But this is not always true. Here, for example, we have to define first the meaning of an absolute extrema. Well, the f of c, where c is element of the domain of f, is called an absolute maximum of a function f if for all x element in D of f, f of c greater than f of x. Here you don't have to have an interior point. You may have a global extrema at the endpoints, because since they lie in the domain of f. There we couldn't, because we are relying on the derivative of the function, and the derivative of the function can actually occur at one endpoint from one side. Since it occurs at one side and it may not be zero, so it's not a critical point, because the critical point is a point at which f that either it is zero or does not exist. Here it is not zero and it exists because it exists from one side, so we cannot consider the local extrema happening at an endpoint. It has to be an interior point. But then here, absolute maximum of a function, it's over the whole domain. You want to find what is the maximum value of this function. So what you do, you scan all the points, you find, and you calculate the value of the function, all these points, and the maximum value of it will be your global extrema, whether maximum or minimum. So the thing which is, and same thing, of course, for the absolute minimum. The absolute minimum of function f is for all x in the domain of f, f of c is the least one. If f of c is the least one, then sure, this will be the global minimum of the function over the entire domain, over its entire domain. Now, the thing which is which comes to mind directly, logically speaking, is that what you do, you may rely on the local extrema in order to calculate the global extrema. What you do is that, for example, you have something like this. This is a graph of a function, y is equal to f of x, and this is a local extrema. Here, this is a local maximum, and this is a local minimum. Since there are no other local maximums, so you say, all right, this is the local, and at the same time, it's an absolute maximum because it's maximum among all values of x in the domain of f. And the same thing here. This is the local or also minimum, and it's at the same time is the absolute minimum. But it doesn't happen all the time that a global maximum occurs at one of the local maximum of the function. It's not true. For example, you may have something like this. This point here is the local maximum. At the same time, it's an absolute maximum. Yet this point here, this is the local minimum. It's a local minimum in the neighborhood of a point in which it's an interior point. Yet the global minimum is not this point, because here the function ends here, and this is the absolute minimum. So now we see that although the local and absolute maximum, they may be same, or the local and absolute minimum, they may be same, one of them may differ. Even both of them may differ. So the absolute maximum is not necessarily one of the local maximum. Neither the absolute minimum be one of the local minimum. You may find an odd situation like this one. Here you have an absolute maximum, and here you have a local maximum attaining at a point C in an interior point here. This is the local maximum. And it's not the absolute maximum because the function climbs, although it goes down, but it climbs again, so the absolute maximum occurs here. Same thing, this is a local minimum, and the absolute minimum is here. So you see now that it's not true that the local and absolute maximum or minimum, in general the absolute extrema, may not occur at all at one of the local extrema of the function. They may differ. So you cannot rely on the tests for finding the local extrema in order to locate the global extrema. You have to scan the whole domain of the function. So in order to calculate the absolute extrema of a continuous function f, what you can do now for the local extrema, it's easy. Why? Because the local extrema, all you have to do is that you locate the critical points. That's all. Local extrema, it's easy. You come and you take all the points at which f dash is zero or it doesn't exist. And since this point lies in the domain of the function and it's an interior point, then you call it a critical point. But you have to make sure to apply the test. Why? Because suppose, for example, you have a function like this one here, for example, x cubed. Now x cubed here, when you differentiate it, you get 3x squared. Now 3x squared is equal to 0 at this point. This point is a critical point. Why a critical point? Because it's a point at which f dash is 0, and it's an interior point lying in the domain of f. But that this point is a local minimum or maximum? No. Why? Because the test tells you that the slope here is positive, and here again is positive. So it changes from positive to positive. So it's not necessarily to find a critical point to say that a maximum or a minimum has occurred, a local maximum or a minimum has occurred. You have to apply the test. So the test now is conclusive. In other words, first you check the critical points, and then you go ahead to check which of these critical points can be liable to be a local maximum or to be a local minimum. Whereas here, the absolute maximum, you have to scan the whole domain. So what we do, in fact, first of all, we only consider continuous functions because they are easy to work with. And in fact, all the phenomena are continuous. So these are the ones that we are interested really in studying. So you have now, we want to calculate the absolute extrema. In other words, the absolute maximum or minimum of a continuous function f. Now we have to know first, is the function defined on a closed interval or on an open interval? You have two possibilities. Either it's defined on an open interval or it's defined on a closed interval. Now, in either situation, you may find that one of the absolute extrema coincides with one of the local extrema. So you are bound to find the critical points because it helps you later on. So now we have to consider one of them only. For example, we consider the case where it is defined, the function is defined on a closed interval AB. So what you do, you have to what? You have to check the endpoints, and you have to check the local extrema in between, and then you decide. So first of all, suppose f has no critical points. If f has no critical points in this closed interval, then it means what? It means that there is no point at which f dash is 0 or does not exist. So f dash means what? It's either positive all the time or negative all the time. So the function keeps climbing or decaying or decreasing. So sure there won't be any local extrema. So the maximum would be where? Would be either here or there at the endpoints. So if the function has no critical points, then sure, the absolute maximum will occur at either the point A or the point B. Because since it is not, f dash is not equal to 0, so it will be all the time increasing or decreasing. So the maximum occurs only at the endpoints. If it is defined, if f is defined on closed interval, and yet there are no critical points. But if it is defined on a closed interval and there are critical points, then you have to check at these critical points because you don't know the value of these local extrema. They may be greater than f of A or f of B. So what you do here, you have to compare these critical points, the value of the function at these critical points with the value at the very end, A or B. So what you do is that since f has critical points in A, B, so you have to what? To let M, you scan all these local extrema at all these critical points, and you choose the maximum one of them as well, and you choose the minimum, the lowest of them, and you compare them with the one in at the very end, at either the end A or the end B. So what you do, you have absolute maximum. You compare the absolute maximum will be the maximum among what? Among the maximum value of all the local extrema, and you whether it is M, which is the maximum among all local extrema, or whether it is one of the values of f of A or f of B. In other words, you take the maximum among the three choices, f of A, f of B, and capital M, or small m for the absolute minimum, and f of A and f of B. Now, if you have an open interval, now it is the same thing. You have to check for the critical point. Now, if you have an open interval, and the function has no critical points, what do you suggest? The function keep increasing or decreasing and has no end. So sure, there won't be any maximum or minimum. This is understood. Exactly. There are no absolute extrema. But if the function has the critical points on AB, then the problem is that the function may go without bound. It may have an asymptote, for example, because it's situated on open interval and it goes without bound. But then the local extrema constitute one corner point at which you have to check. You have to check whether you have, for example, a local maximum, but the function then goes to infinity. So if you take the limit from the left-hand side at B or from the right-hand side at A, and you compare them with these local maximum, then you may decide whether the function has a global extrema in this open interval or not. So what you do really is that you have to check if you have critical points, is that if you have, let m be the maximum value and m is min at these points, and then you compare these values with the limit from the right-hand side at the point A and from the left-hand side at the point B, because the function may do this. The function, for example, may do this here. The function, you have an asymptote here, and you have an asymptote here, and you have here, this is a local minimum, but the function may go like this. Look, it may go like this, in which case, this point here at which, although you better, it's not correct. It may be like this. So here you may have an asymptote, and here you may have a local minima, but this local minima is higher than because the function goes to infinity. So actually there won't be any global minimum because it goes without bound, and the same thing here. So you have to check the limit at the point A from the right-hand side and the limit at the point B, and then you know whether the local minima or our maxima exceeds these two values of limits or not. If they don't, then the function has no limit, and if they do, in which case, if they don't, if the function, if these is higher than this one, that the limit from the right-hand side, that this will be the global maximum. If it is lower, then the function has no global maximum. So here, as it is here, what we do is that you take the maximum of the limit from the right-hand side and from the left-hand side at B, from the left-hand side at B, from the right-hand side at A, and M is an absolute maximum, in which case, if M is the maximum among the local extrema and is greater, then of course M is an absolute maximum. Otherwise, the function has no such global maximum, and the same thing with the minimum. Now we can take an example. For example, they ask you, for example, maximize the area of this rectangle subject to, for example, the perimeter is equal to 100. This is a very simple exercise in which we want to practice the results that we already explained. Here you have the maximum. What you do is that you can substitute for y in terms of x. You get this function here, and you know very well that x cannot be more than 50. Why? Because 2x is less than 100, of course. So you have here now, you have a function which is x times 50 minus x, and you want to maximize it subject to you have x greater than 0 and less than or equal to 50. So you have what here? You want the global maximum of this function in a closed interval. So what you do, as we applied our test, all you have to do, you search for the local maximum, and you compare them with the value at the end points 0 and 50. So first of all, we differentiate this here. When you differentiate, or as a matter of fact, here I followed a different route, is that I wrote it in this way. So directly you can notice that when x is equal to 25, this is the value at which, because you have here a negative sign. So sure, when you have x is equal to 25, the function reach is maximum. But if you want to go step by step, in other words, systematically, what you do is that you differentiate it, you set it to 0, you get x is equal to 25, you substitute here x once is equal to 0 and once equal to 50, you get at the both ends equal to 0, and then at the point 25, you get what? 625. So 625, this is the local maximum, and it's greater than the ones at the very end, so this must be the global maximum of the function. And of course, if you want to make sure this is one local maximum, so it must be a global maximum or a global minima. And here you find that if you differentiate it twice, you get a negative expression for y double dash, meaning that you have a global or a local maximum, which is a global maximum, because you have here the local maxima constitute the same global maxima, because at the very both ends it's maximum than the value of the function at these two ends. This is another example here. You have a function like this one, and it's nice because we restricted the interval to be less than 1 and greater than or equal to -5. So here we have from one side 1, you have to check the limit, and from the other side you have to check the endpoints. So first of all, we determine the derivative, and directly here you have you can check the critical points. The critical points at the point 0 lying in the domain of the function, yes, and then the point also 3 and minus 3, but 3 lies outside the domain, so it's not interested. You are not interested in 3, but so you have how many points? You have the points 0 and the points minus 3. These are the critical points in the interval from minus 5 to 1. And you have to check also the value of the function at the extreme point, which is minus 5, because this is the end of the interval. So we check at minus 5, and we check at the critical points, and we check the limit from the right-hand side. This is exactly what we do according to the test and the results that we have already explained. So here, the critical points are, as I said, minus 3 and 0. We calculate the value of f of x. We obtain 17, 1, and 10. So it seems that 17 is the local maximum of the function. I'm sorry, it's the global maximum of the function, especially that you have to search for the limit of the function at the point 1 from the left-hand side. You find it equal to 9. Since it's equal to 9, so this one here, the value at minus 5, which is 17, this is the one that you will consider at absolute maximum. Of course, had there been the function defined on the closed interval from 1 minus 1 to 5, then you wouldn't have been able, or there is no necessity to check the limit from the left-hand side at the point 1. But because here the function, the interval is open, so you have to take the limit. We found that the limit is less than 17, so the absolute maximum is 17. And we found also that the limit is less than, the limit is greater than m is equal to 1. If it was less than equal to 1, then it would have been different. Here m is equal to 1, so m is less than the limit from the right-hand side, from the left-hand side at the point 1. So sure, this would be the absolute minimum. So now we came up to the end of this lesson, and here we have explained the concept of optimization. Optimization means that you have to optimize a certain objective function, and you have an objective function, you wish to find the maximum or minimum. Now you have to consider two different things: a local minima, or a local extrema, and a global extrema. Now the global extrema means the maximum among all possible values of the function on the domain of the function. Whereas the local extrema means that there are extrema, but in a certain small intervals only. In other words, the function may have many local extrema, but one global only extrema. So in all the tests that we exposed, that we have explained here, we have studied the function were continuous, and for the local extrema, you have to search for the critical points. Once you can locate the critical points, then you check the value at which these points, the value, the change of the signs of the derivative. Either you rely on the sign of the derivative or the second derivative, if the second derivative exists at this point, whether it's positive or negative. Whereas for the global extrema, what you do is that you have to search for the maximum or the extrema among all local extrema, and at the same time you have to search for the ends. In other words, local extrema exist at interior points, whereas global extrema occur all over the domain of the function. And with this, we have in fact tried to explain one very important application of calculus, and one of the even most widely used and found applications, whether in economics, engineering. You always have an objective function, and you wish to find the values of variables that can extremize, that can make this function maximum or minimum. And this is, as a matter of fact, is one of the most interesting and rich problem in calculus. So with this, we have come to the end of our lesson. I wish to thank you for your attention and remind you again, like we did all the times, that all these lessons are uploaded to the platform or the site of the Unitunno Telepathic University. And until we meet again, I thank you very much.